itch like that?
Just some stuff in there.
Have you got any antihistamine?
I don't think I do. I check and see. I don't think I do.
I've had about 7 or 8 bites. I don't know where they got me.
Harold, we hear you. Open mic.
I know it could be out there somewhere.
There it is.
I was only sat.
Oh, good job.
Okay, where were we?
Stay there.
I don't want to do end. How do I get back?
Control tab.
What?
Hit control tab and cycle.
Ah. Except I want to be full screen. We got 2 mores going on. What's going on?
Oh, you're viewing the window that you're viewing. Oh, just click it. Might want to just stop sharing and start again.
Maybe I wasn't sharing.
I think you are. Aren't you?
All right. And I think we're recording. No, what's going on? It's funny. Can you guys see the screen?
Yes.
Okay.
I can.
Except it's not responding. Something's messed up.
I think you're viewing the Zoom meeting, not viewing your slide deck. Maybe, but being at the top there. Yeah, first, supposed to read it, and stop sharing and reach there. Don't be low technology.
No,
It's that capture about that.
I don't have a stop share button. That's my problem.
There you go. You get to-
Huh?
What program is the program? If you put your mouse on the bottom window, what program are you actually in? It looks like you're in Zoom instead of. Yeah, escape will accept it with next to yeah, that's the station.
I don't know. I am recording. That's nice. All right. I stopped the share. Let's try it again. Where were we? 5. That looks better.
Yeah.
All right. There we go. So we'll talk about dynamic range, intermodulation, and cross modulation. The third order intercept, which is always fun, desensitization, which I can't pronounce, preselectors again, sensitivity, and link margins. One of the main receiver specifications that's used is blocking dynamic range. And it's the amount of range from minimum signal to maximum where you have what they call a 1 dB compression. So you get as the input signal increases, you get a linear increase in your output signal up to a point where it starts to tail off. And at the point where it's 1 dB below where it actually should be, that's what they call the 1 dB compression point. So whatever the range is in dB between that maximum signal and the minimum signal is your blocking dynamic range. Effectively, it's the useful amount of dynamic range you have on the receiver. Because once you get up to the point where you're starting to compress the signal, you really don't gain anything. There's a little diagram showing normally if you didn't have any compression, you'd follow this line up to infinity, which in the real world you can't do. So at some point you start seeing the amplification start to tail off. So at the point where it's 1 dB down, that's where you actually measure the upper point to determine the blocking dynamic range. So what is meant by the blocking dynamic range of a receiver? Intermodulation. You have these mixing products and you get some that you don't really want as a result of that, and they call it intermodulation. It's really just a result of mixing in a nonlinear device. In this little example, you've got two signals, omega 1 and omega 2, coming into the nonlinear. That's what the little curved line indicates, amplifier. So what you're going to get out is omega 1 and omega 2. And then the sum and difference products, which would be 2 times omega 1 minus omega 2 and 2 times omega 2 minus omega 1. Those would be actually the third order products. You care about those because it turns out they're the ones that are closest to your original frequencies, where the second order harmonics are farther away. It's one set of the third order harmonics, which turned out to be adjacent. And that's why we're going to talk about the third order intercept, because it's the third order products that are the ones that are hardest to get rid of.
What do alpha and A represent in that graph with the yellow arrows?
I knew somebody would ask that.
Good. That means you have an answer, right?
I believe that those are referring to the amplitudes and the Fourier coefficients when you do that Fourier transform, and that's how you actually get the actual amplitude of what those product signals are. That's just my guess. I haven't worked it through, but normally that's how you take the discrete Fourier transform coefficients, and that's how you figure out what the amplitudes are going to be on the various frequencies.
Since college, so
Yeah. Well, you don't have to do it here either, but you're supposed to know a little bit about it to be dangerous. In the bottom one, we've got two interfering signals, and what our passband or channel is that we care about. So if those are coming through that same nonlinear amplifier, you can see that one of those mixing products can wind up in our passband that we don't really want. So what causes intermodulation in an electronic circuit? Okay, here is a display of a bunch of the mixing products. So F1 and F2 are where we start with two different signals. And you can see that the third order products are this bunch down here and these two over here. These are the ones that cause the problem. The two F1 minus F2 and two F2 minus F1. The third order up here is easy to filter out. It's pretty far away. The second order harmonics are easy to filter out. These are not. So that's why you try to suppress them as much as possible. But you need to remember the two F1 minus F2 and the two F2 minus F1. So why are odd order intermodulation products created within a receiver of particular interest compared to other products? I'd say alpha looks good. Okay, here's an example. So I've got a receiver and I tune it to 146.7 megahertz. I got a nearby station that's at 146.52. So if I have some nonlinearity, I can actually hear signals on 146.34 and 146.61, which are a result of those intermodulation products. So if you remember that, and I just used F3 to represent these, the two F1 minus F2 and two F2 minus F1, which are those third order products that are going to be adjacent to your signal. So we're tuned to 146.7, okay? So if I solve for the two F2 minus F1, but I don't know what F1 is. So if I solve it for F1, okay, it comes out to 146.34. So that's one of them I can hear because it'll wind up being in the passband. In this case, I'm trying to find what the other one might be, where I still know that my frequency I'm tuned to is 146.7. So I do the two F2 minus F1. When I know F1, I don't know F2. So when I solve for that, then F2 turns out to be the sum of those two divided by 2. And that's where I get the 146.61. Clear as a bell, right? It's just simple algebra. Yeah. It's hard on the test, though. Because there is a test question.
Just one?
One like that. Like this one. So I'm tuned to 146.7 and I got a station on 146.52. What are the two intermodulation products?
Yeah.
How's your short-term memory doing?
Right now, not very good at all. And that's all just a bunch of numbers.
But we just worked through it.
Same
It's
numbers.
probably alpha, then it's
Probably alpha. Now, if you can remember those two, you don't have to do the math.
yeah, that's right, because that is the question.
Yep.
So E4D05 is.
But it won't be, not necessarily A.
3461.
That's one of the harder problems.
It's only hard if you don't know anything about it.
Well, that makes it harder.
Yeah.
I don't think it's easy even if you understand it. You got to do algebra.
Well, that is okay, but
Okay.
remembering these F2s and F1s and.
Well, it's just, you know, 2F2 minus F1, 2F1 minus F2.
There's no DBs involved.
No DBs.
It's about as clear as DB, but that's.
You can also get intermodulation in your final amplifier or power amplifier. One of the causes is you can get, since you got an antenna, even though you're transmitting, that antenna is still receiving signals, which can feed into your final amplifier. Now they take care of that on repeaters by using a circulator. So if you got a signal coming in on the antenna that you're transmitting on, the circulator feeds that back to a dummy load, as opposed to letting it get into the repeater. In your 7300, you don't have that. So if you're transmitting, you can still get signals in, and they can mix in your final amplifier with your transmitter. So you can actually be transmitting spurs as a result of that signal coming in.
So you're transmitting
Mm-hmm.
a signal at 100 watts
Yeah.
or whatever.
Right.
Kilowatt. And
And you got some milliwatt signal coming in on the antenna.
well, it's completely wiped out by that kilowatt signal that's going out.
Well, but you're going to get a mixing product, which has got some power, which is at a different frequency. And it's being transmitted by your 100-watt transmitter.
Like the amplifier section on final output of your radio is normally only going to amplify what's coming from the transmitter oscillator in your radio. The problem here is that if you've got another nearby signal that's oscillating, let's say you're trying to transmit on 146.52, and you got a repeater sitting at 146.61, and it's putting out 100 watts, and its antenna is only a few feet away from yours, so you're trying to transmit out on 5.2. That repeater output is going to put RF energy into the antenna that you're transmitting out of. That received signal is going to come back into your final amplifier stage, and so it's going to see not just your 146.52 input from the local oscillator, it's also going to see the .61 coming in from the external antenna, and therefore your final amplifier section is going to amplify both frequencies at the same time. One of them a lot stronger than the other.
Your amplifier's actually becoming a modulator because you've got the signal that you're transmitting, and then you've got the one coming in that's going to actually modulate and mix with that signal. So you're actually going to retransmit these other products. Now, granted, it's probably low level, but they're still out there.
So the transmitted signal is not going to blow out, so to speak, the little tiny receive.
No, it's a different frequency.
It's not a receiver in your radio that's the problem, it's the final amplifier stage that's actively transmitting.
Yeah, so it's not receiving anything.
Right.
It's receiving.
But, well, it is not your receiver, but the transmitter. Okay. You've got your transmitted signal and another signal adding to it, which is acting like a modulator if that's a nonlinear amplifier. And it's going to have some nonlinearity. I mean, there's no such thing as a perfectly linear one.
So to get rid of that you'd have to put a very narrow filter.
Well, that's why they use circulators on repeaters. We'll get to that.
At transmitter sites, they use either circulators or narrowband filters when it's a fixed frequency. If you're floating around, you can't do that very well,
Right.
but. And it's broadcasting facility where you've got 5 or 10 or more transmitters running at 50,000 watts or something. You're gonna have circulators and you're gonna have bandpass filters that are sitting there saying, okay, my output frequency, this cavity filter is only tuned to allow this output frequency. So that also keeps it from anything else getting back in to the transmitter.
And we'll talk about cavity filters too.
Bob, I got a question about amplifiers. Aren't most of the modern solid state amplifiers broadband, where the old tube types were typically tuned output?
Yes, most solid state are wideband amplifiers.
So they're more subject to intermod than the older tube types.
I would guess so.
Okay, just curious. Thank you.
Okay, so. A received signal on your transmitter can cause intermodulation. How much? I don't know. Then we talked about a circulator, which it's kind of like a directional coupler. I don't understand how they work either, except it's able to direct signals. It's a 3-port device. So I have the transmitter connected to it, I have my receiver connected to it, and I have a dummy load connected to it. So the way it supposedly works, if I get a received signal on the transmit line, it routes it to the dummy load. If I'm transmitting, it routes it to the antenna. If I'm receiving in receive mode, it goes from the antenna to the receiver.
It's only VHF.
I don't think so.
They work in broadcast.
It's the same problem.
But, yeah,
It's not HF.
Well, I don't know of any high power HF stations.
yeah, you wouldn't usually have.
Well, I'm running 100 watt, that's pretty.
Well, yeah. I mean, and repeaters are normally not more than 100 watts.
Right.
I mean, if you were operating, well, what happens when we operate here, we've got multiple stations, you got a rotator up here, you got a dipole out there, if you're putting out 100 watts each, you could probably experience it. Because you're working HF in close proximity to another transmitter. But if somebody at their house probably isn't gonna have this, because they're probably gonna be doing single frequency. The physics problem probably holds across frequencies. The question is whether it's a practical problem. And at a transmitter site or an antenna site, you're gonna have lots of broadcasting facilities there.
But that's this is the reason why you have circulators on your repeater.
Well, you talk about circulators, but is that a box or is that? What is it? Never heard of a circulator other than a water pump.
I don't think I added a picture. I have one somewhere.
What's in it? Just
Magic.
password?
Magic.
Smoke? It's got the magic smoke.
I've only seen like block diagrams. I don't know. I haven't actually physically seen a circulator. Sherrod has.
I've seen them, but I can't describe it. I'm looking to see if there's pictures.
It's just a thing. It's got ports on it, and that's the way it works.
And do we use that in ham radio?
You have one on your repeater, the club,
Oh,
I'm sure.
There's one, if you go over there, there's one on the floor, right?
Where, in the shack?
Those are the
duplex.
duplex. And that's just a sharply tuned IQ filter.
Well, it's more than a filter. It splits the signal.
And
It's a duplexer.
It can be something very simple like that. not big. It's just got some internal electronics to take the signal, the dummy load's gonna be down on one of the ports, and so the antenna will be on one side and the transmitter will be on the other. And it's just gonna chunk the load down towards an actual dummy. Chunk of incoming
You can
lines.
say that over there.
On your, I'll bet you have one on your repeater.
Well, this is a picture I showed him, just a simple,
Yeah.
small low power device.
Yeah, just, yeah, surface mount circulators. That is
Yeah.
Google's stuff here.
Well, yeah, so it really just one guy wants to work the application of, we may not have a circulator here, honestly.
Well, you may not, but
We may have a filter on it, which is gonna basically.
Yeah,
That's a question.
The difference is that it's gotta dissipate the energy somewhere, the filter is gonna basically take it out. The circulator is not bandwidth sensitive.
well, duplexer just splits the signal. You get two different
Yeah.
frequencies.
One goes to the transmitter.
Well, I shouldn't say it splits it. You get one frequency out here and the other frequency out there. Or a triplexer, you get three. I have a triplexer on my 7610 because it does 2 meters, 70 centimeters, and 23, whatever it is. So you can drive three different antennas or one antenna that does all of them.
I guess I don't know. So that's.
Okay. Write that down. Ed doesn't know what he's talking about.
Right, yeah, I remember.
Which of the following is used to reduce or eliminate intermodulation interference in a repeater caused by a nearby transmitter? I think we probably know this one by now. Even though we don't understand it, you know the answer, right?
Yeah.
What creates intermodulation interference between two repeaters in close proximity? I think I had this chart on there before. So nothing's changed except, oh,
Yeah, second, third.
third order intercepts is why this is here.
Yeah.
So. If we have some 40 dBm input signals, and we have a third order intercept of 40 dBm, it means that those two signals are producing a third order intermodulation product where the third order product is equal to the primary at a level of 40 dBm.
Below the level.
No, they're equal because the third order product increases at 3 dB slope, where the other one increases at 1. So at the point where they intercept, and it'd be easier to see on a like the next chart.
Yeah.
And that's why they call it the intercept, even though it's kind of a theoretical point because they never really get there. Don't have the chart yet. It's coming up. What does a third order intercept level of 40 dBm mean with respect to receiver performance? Charlie? Yep, where they're equal.
You can't do that.
Can't?
You can't ask a phone a friend thing, sorry.
No, it's fine.
You'll have to come up with your
The
own.
life's line. Here. I'm not gonna waste my call on that.
Where'd my chart go? Either that's on another section or I know I put it in there.
That weird circulator thing.
Yeah.
Essentially,
Desensitization is where you have a strong signal and it's actually sort of overloading, and it reduces the sensitivity of the receiver for other signals. So one of the reasons is poor dynamic range. The wider your dynamic range, the less that effect is going to be. And I guess if you narrow the bandwidth, you have less effect. It's still one of those kind of, it's a question on the test. I don't know where you actually run into it.
I can tell you I've run into it.
Yeah.
Another amateur and I were both within visual distance of each other, driving on the road near one of the local stores. We were both talking on the 6-1 repeater. When he would key up, I couldn't hear anything off the repeater. I'd key it up, I'd unkey, anybody else would talk, I could hear other people talk on the 6-1. He would key up, my radio would just act like there wasn't a signal at all, because he was desensing from the local transmitted output on the offset 146. Transmitting at 6.7, and the RF energy of that was desensing my receiver so much I couldn't hear 6.1, because it's like, oh, I'm going to turn the AGC way down because I got too much signal here. I can't hear anything at 6.1 anymore. So that was the first time I've actually experienced it in person. Was just because of other RF energy outside what I was trying to hear. So desensing the front end of my receiver.
Yeah, it just happened to me. I was at a light, all of a sudden I got killed in it, and looked over, there's Dan, and one of the, this radio.
Yeah, it just wipes it out. So that's the first time I've heard about it, I've known about it, I deal with it in my business or work stuff, but that's the first time I've actually seen it on amateur.
Yeah, we both lived in the same neighborhood, we just happened to, same.
Yeah.
I don't know where my chart is for that one either. So what's the term for the reduction in receiver sensitivity caused by a strong signal near the received frequency? Which of the following describes problems caused by poor dynamic range in a receiver? The only one that makes sense.
Yeah.
Which of the following reduces the likelihood of receiver desensitization? Be a good guess. Pre-selector we talked about before, where it's just essentially bandpass filters on the front end so that you're attenuating out of band signals. So what's the purpose of the pre-selector in communications receiver? Link margin. It's the difference between what they call the minimum expected power that you receive compared to the receiver's sensitivity. So the minimum discernible signal is one limit, and the minimum expected power that you're going to be receiving, and that difference is your link margin. And you normally want that to be in the neighborhood of at least 10 dB. I think down here they say 2 to 3, but that's pretty small because you can have more variation than that. So if you calculate, somebody's transmitting at 100 watts, their effective radiated power with the antenna gain, the losses the path loss to get to you, all those gains and losses in the system, and the signal level that you're actually going to receive, and what the difference is between that and the minimum signal you can detect is your link margin, and then you throw in whatever your signal to noise ratio is down there too.
They're the same as link budget.
Yes and no. It's part, the link budget is where you add them all up. The link margin is after you've done all that, what's the difference?
So you do a link budget in order to achieve a certain link margin that you want or need.
Right.
So if you want to have a 6 dB margin, you calculate the whole link budget, find out what your minimum is, and then make sure you transmit enough power and add enough antenna gain on either end so that you achieve the desired margin. It's part of it.
And the link margin is basically your headroom.
Yeah.
What they would call in audio. Because things change, your path loss may change. If you're doing refraction, propagation, it's not constant.
Yeah.
So what is the link margin in a system with transmit power of 10 watts? A system antenna gain of 10 dBi, a cable loss of 3 dB, a path loss of 106 dB. What did I say?
106.
Oh, I thought I said 136. Excuse me. I meant to. A receiver minimum discernible, that's what I heard anyway. A receiver minimum discernible signal of minus 103 dBm and a required signal to noise ratio of 6 dB. So it's just add and subtract. But it would be hard to guess the answer.
I bet there's a way to add and subtract all those numbers. It's going to end up with.
But I'll give you a clue. If you came up with a negative link margin, you're in trouble.
Yeah.
They go work together.
Yeah, that's not what you should do.
$40 plus 10 minus 3 minus 136 plus 103 minus 6, and you get 8. That's just straight add, subtract. Well, you add the pluses and you subtract the minuses. What's the received signal level with a transmit power of 10 watts, which is plus 40 dBm, right? 1 watt over 30. A transmit antenna gain, I don't know why there's a dash in there, of 6 dBi. A receive antenna gain of 3 dBi. And a path loss of 100 dB. Which makes that a minus 100, since it's a path loss. So what? You got 40 plus 6 plus 3 minus 100.
So these questions are worded so that when you see gains, you add them, and when you see losses, you subtract them. And that's basically what.
That's basically what you do.
Okay.
Blocking dynamic, oh, okay, we talked about blocking dynamic range. Where you get a 1 dB compression. And I still don't know what happened to my 2 charts. Maybe we talk about this again in the next section. I know they're in there somewhere. Intermodulation and the third order products, the basic thing to remember is the two F1 minus F2 and two F2 minus F1. And those are the odd order products, essentially the third order. They don't normally look at the fifth order. I suspect they would be close to, but much lower level. Desensitization is the reduction in sensitivity due to a strong adjacent signal that's not necessarily in band, but it's close enough that there's some spillover, so it's affecting the basically, I guess it affects the automatic gain control because it's seeing part of that signal, so it's going to reduce your gain. Dynamic range due to cross modulation and the desensitization. Attenuation on the front end can help reduce it because you're going to reduce the interfering signal, which is causing the blocking. Pre-selectors help you reject signals outside the band that you're trying to receive. I don't know, did we have anything on sensitivity? Maybe I never went back and filled that in. And link margin is pretty self-explanatory. It's just add up all the things in the path and compare that to what your minimum receiver sensitivity is, and that difference is your margin. All right.